Coming to system neutral earthing, this is single phase transformer, primary to secondary. Primary is 11 kV, secondary is 230 volt, and it is protected by fuse. Here the system neutral, primary system neutral is connected to ground, whereas secondary is not connected to ground. In this case, at secondary, the line to line voltage will be 230 volt at terminal 1 and terminal 2. But the line to ground voltage is very high compared to line voltage. This is because of existence of capacitance C1 and C2. The capacitance formula is E equals to E0 ER A by D. This is the primary winding, this is secondary winding, and this is ground. Here we are comparing the voltages. The primary voltage is very high compared to secondary voltage. So between higher voltage to lower voltage, capacitance will form. The medium in between these windings is insulation. So this insulation will form a capacitance. This dielectric material will form a capacitance C1. Similarly, from secondary winding to ground terminal, here it will form a capacitance C2. Here the secondary winding is at higher voltage compared to ground terminal. Here if we compare the distances between the windings and from the winding to ground, the primary winding and the secondary winding, the D1 is very low compared to the distance between the secondary winding and ground terminal. So from the capacitance formula, C is inversely proportional to distance. So the D1 is very low, so that capacitance C1 will be very high. So from this discussion, it is clear that the capacitance C1 is very high compared to capacitance C2. And general formula Q equals to CV, the relation between C and V, as the capacitance and voltage both are on one side of the equal to, so that the relation is inversely proportional. So for lower capacitance, the voltage will be very high. We take the C2 capacitance. The C2 is very much low compared to capacitance C1. Capacitive impedance XC equals to 1 by 2 pi FC. C2 capacitance we are considering here. C2 is very low, so that XC for C2 is very high. As XC for C2 is very high, the voltage will also be very high. Terminal voltage Vx with reference to ground, for this XC, the voltage may be around 5 kV. So if any person makes contact with any of these terminals, he is directly connected to the ground and the terminal. Distance is approximately 20 kilo ohm, and the terminal voltage is 5 kV because of the capacitance, and the system neutral is not grounded. So if we calculate the fault current, 5 kV divided by 20 kilo ohm, this is approximately 0.25 ampere. If we take the value in milliamperes, it is around 250 milliampere. As we already discussed, 10 to 20 milliampere, the person may get severe shocks or fatal accidents. So in comparison to this, 250 milliampere is very high. This is the case when the system neutral is not grounded. The system neutral, in general terms, generator neutral point or transformer secondary neutral. In this case, we have considered single phase transformer. We can also consider three phase transformer. In both the cases, the condition is same. Single phase means only one phase in a three phase winding. Three phase means all the three phases are considered, but the neutral is common. This is the case when secondary of the transformer is not grounded. What are the effects? Here is the fault current calculation in this case. We'll take the second case, the same case where the system secondary is grounded. In this case, The line to line voltage is 230 volt. The terminal 2 is directly connected to ground. The voltage here is 0 volt. If a person makes contact with the terminal T2 where the direct grounding is provided, technically he may not receive shocks when the system is not loaded. And if a person makes contact with this terminal, the fault current will be 230 divided by 20 kilo ohm. This is around 11.5 milliampere. This is the case falls between 10 to 20 milliampere case. He may receive severe shocks or fatal accidents. So comparing these two cases, when system secondary is not grounded, when system secondary is grounded, in this case the fault current is very high. In this case the fault current is very low compared to ungrounded system. In grounded system the fault current is very low. In ungrounded system the fault currents are very high. From the overcurrents, a person may receive shocks. By short circuits, the equipment may catch fire. So in order to avoid these abnormal conditions, protective devices are provided. So during dead short circuit condition between primary to secondary, this is the path of fault current. Because the system is grounded, the fault currents are immediately diverted to ground and the equipment and the operating persons are protected. So these are the important points regarding system neutral earthing in case of single phase system.